this component of the astronomy lecture series is on a very interesting component, very interesting aspect of astronomy, and basically the oldest branch of astronomy. So that this is what people did before all the theories and all the, even before math. So this is very quite old practice in the field of astronomy. So we are going to talk about the observational astronomy. So first of all, I hope you guys can hear me. So if anything goes wrong during the lecture, just drop a message in the chat, right? And also, if you guys have any questions, like anything in between sides or in between this lecture, you can interrupt me and ask your questions. And also, if you like, if you don't feel like talking, you can drop a message in the chat, and I'll answer it. Anything related to this or anything you want clarify. Okay, so let's start. So during this lecture, we'll talk about different types of telescopes. So telescope is the basic tool that we use to observe the sky, apart from our own eyes. So we'll talk about different telescope types, and also how they perform, how their functionalities implemented. So that's that will be the major component of this lecture. And then we'll talk a little bit about celestial coordinate systems. That is basically how we locate objects in the sky. So we know that there are billions of trillions of objects in the sky. So how do we identify them individually? So how do we find them individually? So that is something that we are going to talk about. And also then about the software we use, the modern component, like the 21st century astronomy. So how it's done, how it goes on. We'll talk a little bit about that. And also after this lecture, there will be a little assignment for you. That will be a Moodle, so that the assignment will be based on the astronomy component of this lecture, and also a little bit on actual observation. So pay attention to that part, and also pay attention to the other information on the especially on the celestial coordinate systems component. Right? So okay. So first question, why do we observe? What is the point of observing the sky? Basically, now that we have a spacecraft pretty much everywhere in our solar system, but we still observe the planets, still observe the things beyond our planet. Right? So the most important reason and the most valuable reason today we as amateur astronomers or as professional astronomers do observations is to support theoretical study. So verifying or disputing theoretical hypotheses and models is very important. So the space, basically the objects in the space, are a very good sandbox. Or if you take a very good observation pit for the theoretical, mainly theoretical physics. So that's the major reason that scientists observe the sky. And the other major reason is the studying of our own origins. So how did the Earth form? How did the Moon form? How did the solar system form? So what's going to happen to the planets? What's going to happen to Earth in billion years, in million years, in 100 million years? What's going to happen to the sun? How did the sun form? How did the sun end? So those questions are a key part of the observational astronomy. So people observe the sky, hoping to find answers, at least good enough answers for these key questions in basically natural sciences. And then something else that is also important, that's something we hope will never happen, is identify future threats. So basically planetary level threats, like say asteroids, meteors, or even comets that can affect the life on Earth, affect the planet Earth. Identifying them early on is very important. It's a very important component of observational astronomy today. Apart from this, so this we're talking about the current world now. So a few thousand years back, say a few hundred, even few hundred years back, one of the most important component was of observing sky was navigation. So they didn't have maps, so they didn't have anything to guide them on Earth. So they didn't have maybe they had the very basic compass, but for them, stars was a very important component of guiding in their travels, in their expeditions. So that's what that was also a major component. But today, in the current world, navigation based on stars is a very niche component of astronomical observation. Basically, never done on Earth, on the surface of Earth, but it is done in some other components. So we'll talk about that in a little while. Okay. So let's talk about telescopes. So telescopes are basic tools that we use to observe the sky. Observe the sky means observe the celestial objects, right? So the two major telescope types are optical telescopes. That's what we can see, and radio telescopes. So that is what the radio waves, that's detecting the radio waves. Then first optical telescopes are detecting the optical waves within the visible spectrum. Right? Okay. So if you take a distant object, a faraway object that is sufficiently far away than the focal length of a lens or focal length of a mirror, we can consider the light coming from that object as every light ray coming from that object as parallel to each other, right? So at the mirror or at the lens, we can see a parallel beam of light. If you take the sun is 1.5 billion kilometers away, right? So that distance is enough, considering the size of the sun. That distance is enough to say that all the light rays that are coming from the sun are parallel to each other, right? So that is why we can focus the sunlight into a single point using a simple lens. So that is the reason. So I don't know whether you have tried this, but I think you have tried the focusing light to a single point using a lens from the sun. So you can light up matches or light up pieces of paper. But have you tried doing that with a light bulb, a household light bulb, or especially a tube light like a fluorescent light? So if you have tried that, you will see that you can point that light into a single point. Even the sun is a massively large object compared to the simple light bulb or simple fluorescent tube. You can focus that light to a single point, right? But if you take a household light or especially filament bulb or like a fluorescent tube, you will see that you are not able to focus that light to a single point. So the reason is that the distance between the lens and the light source is not enough to form that parallel light beam model, so that we can't focus that light into a single point. So that theory has been used in telescopes in many different ways. So basically what you see is incoming light rays can be focused onto a single point, right? So that any object that is far away, sufficiently far away, can be focused onto a single point. So what will happen if the object moves a little bit? So if you think the object moves away from the mirror was or the mirror or the lens was moved or like tilted, the light is still parallel to each other, right? If you can see the dotted lines, they are still parallel to each other, but they are not parallel to their previous form, but still parallel to each other. So they can still be focused on a single point of light, right? So that single point of light, if you take any object outside of the mirror, that single point of light will lie on a two-dimensional plane that goes through the focal point of the mirror. This all similar to mirrors or lenses. The only difference is on a mirror, it will be on the same side that the focus will be on the same side of the mirror, same side from the mirror as the object. But if you take a lens, that will be on the opposite side of the lens. So that is basically the same light pattern, but it's the mechanism is different. So if you place a camera, a CCD camera, or even a human eye here, you can see this object, right? So if you take the light coming from many objects, even though they are in different places, even though they are in different angles, they will be all these lights will all these points of light will be focused on a single plane. So that is why you can see everything in the sky. If you just look up in the sky, what's happening is image of that all the points of light in the sky is formed on your retina, right? So that can happen because they are number one, they are sufficiently far away, and the other reason is that the lenses that I can focus the light onto a plane. So how is this different from a normal camera? Like if you take photos of, like if you take a normal camera, a phone camera, or a DSLR, how is this different than that? So the reason is basically there is no depth of field for the objects. So they all seem like they are at the same plane. So what we can see is what we see on the sky is that single plane of objects that is surrounding us, right? You can't see the difference between two stars. The length difference between two stars. So one star may be like 5 light years away from you. Another star will be 500 light years away from you. But what we can see is from the Earth is that they all are on the same plane, right? Same sphere. We don't see the depth difference between them. So that's why there's no depth of field for sky objects, right? Because of this reason, a single mirror with a fixed focal length can focus objects, can see any object, can image any object, can focus any object onto the eye in astronomy. So that's why I went through all this light ray theories and light rays, what they are doing and parallel pictures and all that. The reason is that if you take a camera, good camera, or optically good camera, it can focus on a single plane. That's it, right? You will see the objects on the focused plane in very clear detail, but everything else blurred out. Right? That is the depth of field. That is because all these objects are terrestrial objects. All these like our everyday objects have depth of field because they are basically at a finite distance from the optical components of our eye or optical components of our camera. But if you take the sky, everything is in a single plane because they are sufficiently far away. So this theory is why telescopes work. Basically, the answer that why telescopes work is not how telescopes work. This is the basic theory of why telescopes work, because it's just a single focal length camera, basically single focal length camera that can see everything. Right? It can see the moon, which is like 250,000 kilometers away. It can see a galaxy that is 1,000 light years away. Right? Both will be in focus. In a telescope, everything will be in focus, right? So that is the reason is they are sufficiently far away that there's no depth of field for sky objects, right? And so I hope that makes a little sense as a beginning. So let's see what optical telescopes are doing, right? So there are basically two types of optical telescopes. One is refracting. So basically refracting is light passes through a optical element. So basically a lens, and the other type is reflecting telescope. So that means light is reflected from an optical element that is a mirror, right? So if we take refracting objects, so both these telescopes have different constructions, different characteristics. We'll talk about that, but let's see. So what it is if you take a refracting telescope, it's basically a lens that is focusing light onto a focal point, right? So so there are problems. So if you take a lens, you can't fix anything to the center of the lens, right? You can only fix a frame to that. So you can only support a lens through its edges. Right? So then the problem is that the size of the lens is going to be limited. So it's going to be glass. So glass is heavy. So that the maximum lens that can be manufactured is going to be limited by the strength of the basically the tensile strength of the glass, right? So it's by design, glass lenses are restricted to a certain size, right? So in the old world, like in the early 20th century, this glass limit was hit. So glass manufacturers, lens manufacturers, and telescope manufacturers came across this limit that is 100 inches. So when the measurements are on inches, so they realized that the largest lens they can manufacture is 100 inches without deforming the lens during mounting or during moving around. Right? So that was a massive problem for the optical and refracting telescopes. Another issue is chromatic aberration. So chromatic aberration is an optical problem. So that optical basically optical fault that happens in glasses. We'll talk a little bit about that in one of the next slides. So another thing is light is going to be absorbed. So if it's a refraction based optical system, definitely light will be absorbed through the glass, right? So the real problem is that this absorption will depend on the construction of the glass. So different materials in glass, like if you have sodium in glass, sodium salts in glass, it will absorb different wavelengths. So if you have something like lead in glass, it will absorb a completely different set of wavelengths. So that depends on, so that light absorption is not uniform. It depends on the type of glass. So that is going to be a problem for astronomical observations. And the other part is the glass is a very complex optical component to be manufactured. So it has two very smooth, very smooth surfaces that has to be optically perfect, right? There can be any ridges, there can be any imperfections and anything. And also inside the glass, since light is traveling through the glass, there can be any air bubbles or any imperfections or any tensile stresses, right? So because of that, air bubbles will affect the image quality from a refracting telescope. So that means good lenses are going to be expensive. Good lenses are going to be small, and they are also going to be expensive. So the solutions to this is the reflecting telescope. So a reflecting telescope is basically a curved mirror that has only one optical surface. So light doesn't go through that. So only one surface has to be perfect. And also, so likewise, the other surface can be a supporting surface for the mirror. So the mirrors can be supported from behind. That means larger mirrors can be constructed, and larger mirrors can be mounted on telescopes without too much trouble. And also, light doesn't go through any optical object, right? In a mirror, it does just reflect. So that means there's no chromatic aberration. I will talk about chromatic aberration in the next slide. And then the other part is reflects all radiation, so not all light. It can reflect basically all radiation with only a small loss, only very small absorption loss. Like it can basically acceptable mirror. Like I'm not talking about high end scientific grade mirror, like maybe even very commercial grade mirror can reflect about 99% of the light it's met with, right? So that's very good. Optically, that's a very good condition. Okay. So that means reflecting telescopes have an edge compared to the refracting telescopes, if we consider sky observations and their practical use in astronomical observations. Okay, so what is chromatic aberration? I'm sure you guys, some of you might have seen this, and some of you might have even experienced this in photos or in cameras. So that's basically lens focusing different colors at different places. So the refraction through a lens is basically dependent on the refracting index of the glass, right? So glass refracting index is, on the other side, is dependent on the wavelength of the light. So that means different wavelengths. Like if you take blue, that's a shorter wavelength than red. So that means blue light will be focused closer than the red light. That means if you take a normal white light beam coming from this side, the light will be separated into its constituent colors at different focal points by a lens. So correcting this can be corrected using a complex lenses, using many optical surfaces that can be corrected. That means it's going to be heavier again, even more heavier and even more expensive to manufacture lens that can basically that is remedied for the chromatic aberration issue. So if you take a mirror, reflection angle doesn't depend on color, right? A reflecting surface can reflect blue light or green light or red light at the same reflecting angle. So reflection angle is only dependent on the incident angle of the light ray. I think you can remember that from the levels. So that means mirrors doesn't have this chromatic aberration issue. So in the right side, you can see what chromatic aberration looks like in a practical scenario. So that this is what we see through a telescope. So this is basically a star, right? So it may look elongated because of other optical issues, but it has to be a white elongated blob. Okay, so if you take a reflecting telescope, you will see this. It has some other like deformations, but it's still in its true color. But if you take a refracting telescope, you will see that the colors are separated. Its shape has changed, and also the colors are separated into different color patches. So this is not going to be good for any serious astronomical observation, right? So this is basically what a prism does. So a lens can be analyzed as a set of prisms, a collection of prisms. So each prism is going to separate the light it meets it into its constituent spectral components. Okay. So this is basically the physical construction of the telescope. So if you take a refracting telescope, there's an objective lens. That's the main lens that collects the light. So that's what we talked about. This is the lens that has to be supported. Then this is the lens that contributes to the chromatic aberrations and things like that. And then there's a eyepiece lens. This eyepiece is here to focus the light into the light detector. So you know that the main lens is focusing light into a single point, but a single point is no good if it cannot be formed into image, right? So if maybe maybe a camera, maybe another sensor, another color sensor, or maybe a spectroscope, anything like that, the eyepiece lens is going to be focusing that light into the sensor that is used to make the observation. In a reflecting telescope also, it is pretty much the same. There's primary mirror instead of the objective lens. So this is the main light collecting element, and then there's a secondary mirror to fold the light part. So this secondary mirror is a plane mirror. So it's not going to be changing the focal point of this mirror, or it's not going to be changing the focus of the light beam. It just diverts the light beam away from the main primary mirror, so that a sensor or receiver or object observation point can be mounted. So at the observation point, there's another lens that's doing the same thing as this eyepiece lens. So that this is also eyepiece. So that eyepiece can focus the light onto the camera or the eye or the any other device or in any other instrument that is going to be making the observation. Right? So as you can see, after the primary optical operation, so it can be a primary, it can be a refracting through an objective lens, or it can be a reflecting through a primary mirror. Everything else is pretty much the same. Everything else is pretty much trying to get that collected light into the optical sensor, right? So these are two commercially available examples of these two types. So this is the refracting telescope, the commercially available one. So if you can see here is this part is actually shroud, so that the outside light cannot enter the tube except light from the directly up here. So the primary lens is over here, and the eyepiece is over here. There's a small prism here to bend the light part, just like this, just to facilitate the observer. So this is optimized for human observation. So you can use it with normal position. So that's just to facilitate the human observation. So the eyepiece lens is over here. Then you can see through here. In this is the basic, like the most simple form of reflecting telescope. So the primary mirror in this telescope, the primary mirror will be here, right? So this side is pointing to the sky. This is the primary mirror, and in here, inside this, there will be this secondary mirror just straight behind this component. There's a secondary mirror, and this eyepiece is right here. This is the eyepiece. So this is where you see through. Right? So these are the most basic types of these two telescopes, so refracting and reflecting telescopes. So basic theory is the same, but there are a lot of different implementations of this optical phenomena. So let's take a little bit of look into that next. So the reason we talk a lot about reflectors is that they're pretty versatile. So you don't only use them. You don't only have to use them for a so for optical telescope. You can use them for radio waves. You can use them for gamma waves. So you can use them for X-rays. So even you can use them for sound waves. So reflectors are very versatile because they have only sound. They have only one reflecting surface, only one wavefront surface. And the other reason is that the material that is built here has very little effect. It does have effect. It's not like there's no effect, but it has very little effect on the reflection of the waves from it. So let's talk a little bit about the types of these telescopes. So the first one is prime focus. So prime focus means that the receiving component is right at the focal point. Right? The receiving component is right at the focal point. So what if I tell you maybe like 80% of you guys have one of these on your rooftops? So basically 80% of you guys have one of these prime focus telescopes in your rooftops, right? So what do you think? Yes, this is basically how a satellite TV antenna works. So if you take dial-up TV or dish TV or whatever TV, satellite TV connection, there's a dish, that is the reflector, and there's a LNB, so RF detector right at the prime focus, at the focal point of the dish. So that's basically a radio telescope or telescope, basically a reflecting telescope looking at the satellite in the geostationary orbit, right? And the next type is, so there are other types that basically defined by the position of this receiver, right? So if it's a small receiver, like it doesn't obstruct the wave path too much, it can be placed right at the prime focus. But if you take a larger instrument, maybe spectroscope or large camera, you can place it here, right? You are going to obstruct the view of this telescope. So for that, there are other types. So this is basically the first type of reflecting components. So that is a Cassegrain focus. Cassegrain focus means there's a main reflector and there's a secondary reflector, convex reflector, to divert that light into hole into a hole in the main reflector. So the receiver can be connected right behind that hole, right? But what if it's a massive telescope? So this central point of the mirror or the reflector has to be a structural component. It cannot be a hole, right? So that's offset Cassegrainians. So offset Cassegrainians, the first primary reflection is the same, but secondary reflection is offset to a side to allow the central point of the telescope to be free for a hardware component or a mounting component or maybe a tracker or rotator or something like that. And what if this receiving component is very heavy, so it cannot be mounted right on the telescope? So then there's this prime focus is then again turned into a Cassegrain focus, and then another secondary, tertiary mirror. Basically, a tertiary mirror is focusing light onto somewhere else where this reflector, where this receiver can be mounted safely and with enough stability, because maybe it's heavy, maybe it needs heavy cabling or something like that, and more power, it needs more cabling or something like that. So that's the Nesmith format. So other part is waveguide. So the waveguide is basically a path for the light wave to travel without a significant attenuation. So what we do is there's a main primary reflector and then a secondary reflector, and there's other component mirrors. There are supporting mirrors that bend the light waves and transform it into other formats. Basically, basically focusing and defocusing the light waves into the receiver that is maybe far away from the telescope, right? And the most common one in radio telescopes and the most common one in satellite communication is the dual lobe. So that means the entire primary mirror can be obstruction free. The entire primary mirror can be totally free without any holes or without any mounting sensor mountings. The sensor of the receiver is totally outside the primary mirror, and the secondary mirror is offset to the primary mirror to facilitate that, right? Okay, so that's about telescopes or optical parts of telescopes. Let's see a little bit about telescope mounting. So a telescope is only as good as how sturdy your mounting, right? Because if the telescope is moving, basically the observation is pointless. So there are two types of telescope mount. The first one is the most basic one. It's called the altizimuth. Altizimuth means the mount is basically like a camera tripod. A simple camera tripod that can be either rotated or tilted up and down, right? So that's the most basic form of telescope mounts, right? So the rotating axis that is basically rotating around the horizon is called the azimuth axis, and the tilting axis is basically where the telescope is going up and down. It's around the altitude axis, right? The other type is more of specific for astronomy, or more specific for astronomical observation, right? For that to explain, I think you have basic idea about the motion of the planet, motion of Earth in the sky, in the space. So you know that Earth rotates around its polar axis every 24 hours, right? It basically rotates around the polar axis, going through the north and the south pole. So that means a single star right at the polar axis will stay stationary in the sky. So that's what we call the pole star, the North Star or the polar axis, right? So in a equatorial mount, this one is called equatorial mount because this polar axis, this rotation, this telescope axis is pointed directly towards that star. So that means this axis can stay. This axis doesn't have to move as the sky moves, right? Because that star is stationary. This axis is not going to change, because that's the polar axis. This is the axis. This is the axis around which the Earth is rotated, right? So this telescope can be rotated around this polar axis. So the axis is stationary, axis is fixed, but the telescope can be rotated around this axis. That means this telescope can track a movement of a single object with only moving along a single axis, rotating around a single axis, right? So you will get a little bit more idea about this during the software session. So we'll using the software, so you can see that how the two coordinate systems are working, how the two mounting systems are working. So it will talk about that a little bit in there. So this is a little bit about the commercially available telescope type. So this is a refractive telescope, just like the one we explained before. And this is a Newtonian telescope. So Newtonian is the most basic form of Newton is the most basic form of reflecting telescopes. So just like the telescope we saw earlier, it's here. This is a Newtonian telescope. So there's the mirror, there's the eyepiece. So in the refractive telescope also, it's pretty much the same arc, and this is also the same refractive telescope, right? So there are other types of telescopes that are going to be combination of these two technologies. So I know this is going to be getting a little confusing, not little confusing, maybe a little bit too much confusing, because why do we use these parts if they are so backwards? So they are not very efficient. So the reason is that Newtonian telescopes are long. They are going to be at least the length of the focal length of the primary mirror, right? So those telescopes are going to be quite long. If you take a very entry-level amateur telescope, the focal length will be like 1 meter. So even 1 meter is too long when you are trying to transport it or trying to move it around. That's going to be too long. So this type of telescopes called SCT, so Schmidt-Cassegrain telescopes, remedy that using a primary lens in combination with the primary mirror. So there this part that you see here, the ring type part is actually a lens. So that assists the primary mirror in focusing the light, right? So this circular part is again another mirror, a secondary mirror that is focusing light back into the telescope. So if you go into the university, I'm not sure you are going to have practical astronomy sessions this time, but if you go to the university and you take a look at our telescope, the ENTC telescope, it's this type of SCT, Schmidt-Cassegrain telescope. I will let me see. I can ask professor to at least set up a demo for you, maybe not in nighttime, but even daytime, to see the parts of the telescope. So I think that will be important. So this telescope is basically a reflecting telescope with the lens element to reduce the length. So it's a shortened reflecting telescope. And this one is another type. It's called Dobsonian because it's a relatively modern design, explained from its inventor John Dobson. So it has a longer tube, but it has a different mounting system to support the longer tube. So it's not as much as a hassle to handle like a Newtonian telescope. So these telescopes can be built larger, can be built like even into massive telescopes, and then it also can be used with relative ease in astronomical observation system. Okay, so that's about commercially available telescopes and what we can see out in the field of astronomy. So let's talk a little bit about theories that are behind this optical telescope, right? So basically, for telescope, one of the most important parts is the mirror size. So that means the size of the space, size of the surface that's going to capture the light. So more light, brighter objects, and that means more light, or the larger the mirror, you can see fainter objects with the telescope, right? So that's why this type of telescopes, like observatory gate telescopes, have massive mirrors. So I don't know whether you know this, but the largest telescope in Sri Lanka is at the Arthur Clarke Institute, just across the road with the university. That telescope is 45 centimeters, 18 inches, 45 centimeters of primary mirror diameter. Right. So the size of the telescope is measured with the size diameter of the primary mirror. Right. So if you take like entry level, amateur level telescopes, they are 6-inch meters, 8-inch meters, or 10-inch meters, right? If you go along the ladder, they have 12-inch meters, 16-inch meters, and that's also. So the largest one in Sri Lanka is 18 inches, 45 centimeters. So this telescope, this is the largest telescope in the world. So that's going to be 10.5 meters. That's the mirror size is 10.5 meters. So the largest telescope, you can see the faint objects with the telescope. So how does this happen? So that means, so basically what a telescope does is collecting photons, right? Like these photons emitted by a far away objects. So more photons we collect, more detail we can see, more light we can observe, right? So this is the image of the Andromeda galaxy. I think you have heard of the Andromeda galaxy. So this is the first one is image taken from a 12-inch optical telescope, and you can see some details. You can see some parts, and some parts of the core is very visible, but the peripherals are not that prominent. The outer layers of the galaxy, and this second one is image from a 24-inch diameter telescope. So you can see that with the same exposure time. So same time collecting, same exposure time, same other settings, but only the telescope size is different, right? So you can see there are a lot of other details that are available, a lot of other side components are visible, and also even this is a peripheral galaxy. So this is the main galaxy. This is a galaxy. So it's the closest galaxy to our Milky Way. And this one is actually, it's not a star, it's actually a peripheral galaxy called M101. So that is like a companion to the Andromeda galaxy. So you can even see more detail in here than this one. So that's why mirror size. So basically the light collecting capacity is very important in the telescope. So the one we have in the university is a 8-inch telescope. Right? So 8 inches means 20 centimeter 20 centimeter telescope. And so that's like a entry intermediate level telescope. So there are two main types of observations in today's world. There are two main types. One is imaging, so recording pictures. That's taking images, taking images of galaxies, planets, and everything. So I think that's what you guys have seen, like in most like NASA images, Hubble telescope images, and even like astrophotography images from individuals doing astrophotography. That's one type of observation. The other part is spectroscopy. So spectroscopy is basically identifying different components, different elements in the astronomical objects, right? So if you take light emitting from a star or light emitting from a nebula or a galaxy, that light depends on the composition of that stellar body, right? Different material, different elements, or emit different light wavelengths. So that identifying those wavelengths means identifying the different elements that are forming that astronomical object, right? So, but what we record this is using a camera or a CCD. Right? So a CCD is a camera sensor that can record light. Basically, in a pixel grid, they can record like basically camera, right? What this exactly what happens in a normal everyday camera, but CCDs are mostly this is actually monochrome, so they don't have different sensors for different colors. So there are ways to reproduce colors, but basically CCDs are monochrome, but they are very highly sensitive to photons, light, so that they are used to record either record the images or either record the spectral elements, spectral components from a astronomical body. Okay, I'll show you a photo obtained from one of the from CCD and in a little while. Okay, then the other important part of the telescope is the resolving power. So resolving power is basically the smallest object the telescope can identify. A telescope can differentiate, right? So if you take image of you can just, if you just look up at this guy, the Andromeda Galaxy will be just a, you can see like a blob of just a white blob, like a white piece of cloud, right? You can't see any details. But if you look that through a telescope, you can see these individual stars. You can see these individual components of the galaxy. So that means the resolving power improved. The resolving power of a telescope or any optical system is proportional to the wavelength. So smaller wavelength, smaller the angular resolution, and also mirror diameter. So if a larger mirror, you have a smaller angular resolution. So angular resolution is smaller the better, right? It's basically the smallest angle by two objects can be separated. So you can identify two objects separated by 1 degree. It is better than the identifying two objects separated by 2 degrees, right? So basically, angular resolution is smaller the better. So for a 2.5 meter telescope, so this is basically like a good observatory size telescope. So observing light at 500 angstrom, that is 500 nanometers. 5,000 angstrom means 500 nanometers. So the angular resolution is going to be 0.05 arc second, right? So if you take angles, I think you know how the angle measurement system works. So 1 degree is 60 arc minutes and 1 arc minute is 60 arc second, right? So this resolution, I know that this doesn't have any like meaning on itself, but let's say if you have this resolution, right? So this is a pretty good resolution. Putting that to perspective, our moon is about 30 arc minutes wide. So that's a half a degree wide. So that means this is like you can with something like this telescope, this telescope observing it in this wavelength, you can identify very fine detail in the very fine details in the moon, right? So, but this also this equation is dependent on the condition of the atmosphere also, because all the light waves that are coming from the sky objects has to go through our atmosphere, right? So going through our atmosphere means it's going to be affected by the atmospheric conditions. So there are different atmospheric layers, different reflecting coefficients, refracting coefficients because of the temperature and the composition of the atmosphere, and also there are going to be particles like floating particles, particulate matter in the sky. So that means this angular resolution is going to be affected by the atmospheric conditions. So when we are doing an astronomical observation, when we look up the weather report there, so it definitely has to be clear skies, right, without rain or anything, and also it has to have a very good seeing condition without any air pollution or without any air density variations, anything like that. It has to be very still and also very clean without any particles, right? Okay. For that reason, most of the scientific field observatories and also very expensive observatories are located in very high mountain peaks in the middle of deserts. So the reason behind that is one, the in the desert it's always dry, right? There's no rain or there's no big changes in the climate, sudden changes in the climate. So it's always dry, and so the atmospheric conditions are very consistent in the desert, right? Yeah, and the other part is there are not a lot of human settlements, not a lot of vehicles moving, or not a lot of factories. So that means there are going to be very little atmospheric particles. So I wish I could perform this observation with you guys at the university, because while we are doing the last observation we did was February 2020. Just before the COVID, so we didn't do any observations after that. So, so the point is that if you take Cotopaxi, our location, Morotoro location is it's extremely industrialized area, right? Right next to the Colombo city, there are a lot of factories, a lot of vehicles moving, a lot of emissions. Everything is air is completely full with particulate matter and different air layers, and also a lot of sea wind coming in. Right. That's the one problem. And also Colombo is a very climatically active part of the country. So it's neither very hot or neither very rainy. So rain can come and go quite often. So that means it's a very unstable position for a telescope. So if you take our location in the university, where we do the observations on the rooftop of the ENTC, so we can see the effects of this air pollution very clear, right? So anything below like 30 degrees from the horizon is invisible. The reason is that the air is filled with particulate matter and smoke, and also sea wind coming in, the sea breeze and coming in. There's a lot of salt particles in the air. So that even the sky is clear. Even the sky is very clear. Visibility is very poor in the in our location, our specific location. So for that reason, all serious observatories, like all scientific grade observatories, are either in very tall mountain tops without close by human settlements, or very far away desert landscapes. Yeah, the atmosphere is very clean, and also very stable. Atmosphere is stable. So with all these problems in the atmosphere, there's a solution for this. That is leaving the atmosphere altogether, right? So the most advanced telescopes, most efficient telescopes are not on the surface of the Earth; they are on the space. So the left side is the Hubble Space Telescope, and the right side is the James Webb Space Telescope that this was launched in last year, and went live in last year. So this was the Hubble telescope was launched in 1990. So none of us were born allowed at that time. So this is the part of a nebula imaged by the Hubble telescope, right? So you can see this is the James Webb telescope that went live last year. This is the same. So this is the same nebula component imaged by the James Webb telescope. So you can see the technological difference between 32 years of advancement, right? So if you take the Hubble telescope, this is in Earth orbit. So low Earth orbit, going in our low Earth orbit about 400 kilometers from the surface of the Earth. So still, this telescope has effects from the atmosphere. Still, atmospheric components are present in that height. So still Hubble telescope is not very low, less compared to the surface telescopes, but still affected by the atmospheric concurrence. For that reason, the James Webb telescope is positioned at the away from the Earth orbit, so it's not revolving around Earth, but it's only revolving around the Sun itself. So it's the distance between this James Webb telescope and the Earth is going to be fixed. So it's revolving around the Sun in a parallel orbit to the Earth's orbit. Right? The point is called the Lagrangian point. So that's totally different discussion about what's going on the Lagrangian points. That's basically where object can be placed in a balancing point. It is basically a balancing point between the gravitational fields of the Earth, the Moon, and the Sun. Right? So this is the ideal place for a telescope, because there's not going to be any. It's going to be a very stable point gravitationally, and also there will not be a lot of meteorites, because the gravitational fields, the Earth, Sun, and Moon gravitational fields are going to affect the telescope too much, right? So there's a question: is it from Akila? It's true there's no zero light pollution in the desert, but what atmospheric dust due to winds affect that much into the observations? Okay, so if you take dusty atmospheric dust, that's mostly dust due to winds affect that. Yes, okay. So the dust storms you see in movies and in popular media are only in the Middle Eastern deserts, right? If you take the South American deserts, if you take the Hawaiian deserts, they are deserts. They don't have that much water, or even the Australian deserts, they don't have that much water, and also that they don't have that much dust, right? So that dust storms, dust clouds in deserts are only present in the Middle Eastern desert. So the telescopes I'm talking about are mostly in the South African, Chilean, and Bolivian deserts that are high in the Andes Mountains, and also there are some in Australia and close to Alice Springs, and also there are some in Hawaii, which is basically a volcano. So it is a desert. There's no water. It meets all the qualifications for a desert, but it doesn't have that much of. Basically, there's no sand and there's no sandstorms to affect astronomical observations. I hope that's clear. Even that I know that the image that we get in the result is the wind blowing and the cameras roaming, but that cameras roaming and the sand moving and things like that. So that part is actually in like the Arabian Peninsula. In the Arabian Peninsula, there's a lot of fine dust storms and things like that. But if you move close to Europe, like in Jordan or Syria or places like that, it's always rocky. So that those deserts are more rockier than sandy desert, right? And also, if you move down to like the Northern Africa, then again it's going to be sandy like that. So a little geography lesson for you, but that's basically what different desert climates are doing. Okay, I hope that the answer is sufficient for you. Okay. Yeah, like that. If you have any questions, just drop in the chat so we can keep this a conversation rather than a preaching, right? Okay, so space telescopes. There are some other telescopes also planned for the future, and also different iterations of the JWST or James Webb Space Telescope. Another thing that can be done at space telescope is observing in other wavelengths. So if you take our atmosphere, it does let through the light from the sun, but it does absorb a lot of electromagnetic radiation like infrared, UV, and X-ray, gamma rays. Everything is being absorbed by the atmosphere. So we can do any observations on those spectrums within the atmosphere. Maybe some observations, but they're not going to be very efficient, right? So in order to do that, these beyond optical, let's say beyond optical observatories, so the telescopes have to be placed in outside the Earth's atmosphere, basically in space, right? So this is the Spitzer Space Telescope. It's a infrared telescope, so it can see from wavelengths up from 1100 nanometers to 700 nanometers. So there are the other bands also, but the basic observations are done there. So what it can see is a bit different from the optical component. So if you take a galaxy or a nebula, there may be dust clouds that are obscuring the visible light, but they can let through IR light. So that's what we are seeing here. So this is the left side is a visible light image of the M51 Whirlpool galaxy, and you can see the right side is the infrared view. You can see that there are differences. There are a lot of differences, and also there are details that are not visible in the first one, but very clear in the second image. Right. So that means there are dust clouds that are obscuring the visible light here, but they cannot. Those dust clouds are not obscuring the infrared radiation. So obscuring means basically scattering, right? Basically either absorbing or either scattering. So in order to do that, the particles that are scattering or the particles that are absorbing has to be the same, with basically comparable to the wavelength of the signal, wavelength of the light, right? So something that can absorb visible light that is has shorter wavelength cannot absorb infrared, right? That is lower in longer in wavelength. So that's why different details are visible in different wavelengths. So it will be very prominent here because this is the Trifid nebula, it's a planetary nebula. So what you can see with the visible light is just the dust cloud and the stars that are illuminating the dust cloud, right? So, but if you look at it with the Spitzer telescope in infrared, you can't see anything on this dust cloud because dust cloud is invisible to infrared. So we can see everything behind the dust cloud, like the other components, other parts that are actually emitting light using different wavelengths, right? So this is basically X-ray imaging. So if you take your hand, visible light can't go through your hand, right? What you see is your hand. But if you take an X-ray light source and place it behind that, your flesh and the soft tissue is invisible to the X-rays. So X-rays can go through that, but your bones and the hard tissue is again still absorbing X-ray. So that's exactly what's happening in this different wavelength image. Another one is X-ray. So you know that X-ray is emitted at very high interaction, very high level, high energy electronic interaction. So like in cathode ray tubes and high voltage cathode ray tubes and things like that. So that means if there's X-ray, there's a very high energy, either explosion or a very high energy emission is going on. So that's why the Chandra X-ray observatory is doing. So it's observing this nebula in X-ray radiation. So it can reveal other different components and like different interactions between matter that's only visible in X-ray. So let's move on to something a lot lower in the frequency spectrum of the electromagnetic spectrum. So that is radio wave. So if you take visible light, that's like 100 terahertz range, right? Maybe not even 100 terahertz, maybe even more than that. So if you take radio waves, that's in gigahertz range. So if you take the wavelength, light is in nanometers, 100, 500, 600 nanometers. For the radio telescope, light the wavelength will be in meters, 40, 60, 70 meters. So that means the surface accuracy of the mirror or the surface accuracy of the reflector is not going to be so important. So if it's not perfectly smooth, it's not going to be a problem with the longer wavelength electromagnetic waves, right? So it's easier and cheaper to make a massive telescope, and also it's going to be lightweight. It doesn't have to be premium material. It can be structurally steel or aluminum or something like that. It doesn't have to be glass, or it doesn't have to be like a super exotic crystal material. So it can be make very large and very economic, right? But the cost is the angular resolution. Remember that the angular resolution equation is directly proportional to the wavelength, inversely proportional to the mirror diameter, right? So even if we can make the mirror large and lower the angular resolution, the wavelength will be a million times longer than the visible light, right? So natively angular resolution will be lot less. Okay, so that's a little calculation there. I think you can go through that. Okay, so for this reason, because the mirrors can be made large and it doesn't have too much angular resolution, radio astronomy or radio telescopes can be used to image spacecrafts. So they are going to be really tiny objects, these spacecraft that are far away in the solar system. So you can't see them in visible light or even other wavelengths, because they don't emit light. They only work on reflected light, so that they can be seen, but they still emit radio waves, right? They still emit telemetry data to back to Earth. So the radio telescopes then see them as single points of light. So this is the image of the Voyager telescope taken from a space telescope, Voyager spacecraft taken from a space telescope. So if you know about the Voyager program, those are two. I think you may have heard of them. Those are two pair of spacecrafts that were launched in 1977, long while ago. So they were launched in 1977 to observe the the outside solar system, like beyond Jupiter, Saturn, Neptune, and Uranus and Neptune, right? So they observed them, and then they went on their own ways to outer space. So they went outside the limited solar system. So this is the Neptune, orbit of Neptune, and this is orbit of Uranus, and this is Sun here. The orbit of Earth is even not visible in this scale, right? So this is the current location of Voyager spacecraft, right? So it's beyond our solar system, even beyond the orbit of Pluto, beyond our solar system, and even beyond the Pluto, they are actually in the Oort cloud now, beyond the margins of the sun's. Basically, the gravitational pull of sun is no longer the major force acting on this spacecraft. So the point is that they are very small. They are like few meters apart, few meters across, right? So even Neptune, that is a massive planet, is a small speck in a ground-based telescope. You can see that with the naked eye in any way, but it's also a very small speck on the Earth. It is a massive planet, but still a very small speck on the optical telescope. Pluto cannot be seen from optical telescope on Earth. Maybe in the most advanced one, but not even on like 5-6 meter telescopes, right? But still, a normal radio telescope can see the radio image of Voyager. Right? The reason is that basically the telescope works on emitted radio waves. So if you take the background of Voyager, nothing is emitting radio waves. Radio waves are only emitted by very specific space objects, very specific celestial objects that can actually generate its own energy, right? So for that reason, spacecrafts can be like radio sources can be imaged with relative ease using radio telescopes. So if you take, let's go back to that image of the Andromeda galaxy. So you can see, if you take a visual image, there are a lot of light emitting components, lot of stars and things like that. But if you take a radio image, you can see there are very few specific components that are emitting radio waves, right? So we can isolate those components, isolate those objects, and study them further without the effect of other objects that are not emitting radio waves. That means these objects that are emitting radio waves are much more active or like energy emitting than like all other objects, right? So that's one reason these are being radio telescopes are being used for astronomical observation. So the next part, the reason being that they can be made massive, the telescopes are quite large than their optical counterparts, right? So this Sparks telescope, that this is this one, and green band, yeah, and Great Band. This is in Colorado. This is in Australia. So both these are 1960s designs. They were built in 1960s. So even back then, they can be made this large, right? They were used for the Apollo program also, the moon landings also. And this first work, this is in Germany, run by the European Space Agency. That this is in 1980s, and this was the largest telescope in the radio telescope in the world. This was 300 meters in Puerto Rico, but this one collapsed a few years back, right? So then currently the largest one is in China. I think that's about 1,000 meters wide. The dish is 1,000 meters wide. Okay. So earlier at the very first slides, we talked about different types of reflectors. So you can see physical examples for that, right? So this is the most basic one, GMRT prime focus one. This is the receiver, the detecting element, and this is the reflector. So the reflector doesn't even have to be solid metal. It can be a wire mesh, right? So that's the beauty of radio telescopes. They can be built with very simple material. And this is the one of the telescopes from the Atacama array. One is the Cassegrain focus. So this is the secondary reflector, and the detector is inside here. And this is the this is an offset Cassegrain from the very large array in Smith. And these are the other types of telescopes. Okay, I think you have seen the image of the Milky Way, right? You can even take a photo with the DSLR, basically DSLR from right up to home. So this is what the radio waves see when they look at our galaxy, right? So we can see that the galactic center is very active. There's a lot of radio sources, and it is very active in our Milky Way. So what does it mean? So what this means is that the galactic center is the center of our galaxy is still generating energy. Still stars are being born. Still stars are being evolved there, and also it's still emitting energy that can be detected from here. So that gives the scientists to like observe the actual process of stellar evolution, or observe the actual process of galactic evolution using something like this, something like this observation. Okay, so this something then we come to something quite relatable to us as electronic and telecommunication, especially telecommunication engineers. So I don't know whether these theories are taught now, or it was never taught in nowadays. So have you heard of antenna interferometry? So antenna interferometry is basically mathematically creating a larger antenna using a small array of antennas. So that's basically mathematically simulating a larger antenna aperture using signals of smaller antenna, right? I want you to, I think if you are interested, you can read a little bit on this online. You read about this because it's a really interesting, phenomenon, and it's something that's actually basically electronics engineering. So this has to be one of the most relatable moments between astronomy and electronics. So basically, um, an array of antennas. Let's see. Let's see the next slide. So an array of antennas can simulate or can replicate the effects of a much larger array using something called beamforming. I don't know whether you have heard of it or something. Maybe you have heard of it. Maybe you have used it in. Maybe you're going to use some of that in the FYPs or something. But so beamforming is basically uh, switching between the observable beams. So I'm giving a very vague idea about beamforming. That this is not the definition of beamforming. So that's basically uh, reading different antennas at different times to simulate a larger aperture or maybe a very specific aperture. Right? You should if you're interested, you should read about that. That's a really interesting part of our own practice. Okay, so that's going to be it about observation astronomy. So I hope you got at least a little bit of an idea about how how things how things work and how telescopes are being built and how they are being used, things like that. So I know that you may have you may even own telescopes, but optical telescopes. But I think the radio telescope part is very interesting and it's quite related to our practice of engineering. And also, I don't think you have come across them very often because that's not uh, very talked about, very much talked about in Sri Lanka or even in our university course. So you can read up on that if you are interested. You can go online and read up on what is radio astronomy and what makes this so useful for astronomers. What makes this so uh, why this is such a strong tool for astronomy. And a lot can be done from even from home. Like you don't have to have a massive optical telescope or massive laboratory to do that. You can have simple antenna, simple set of antennas and a small SDR like an arterial SDR or something like that. A small SDR to do radio astronomy at your own home. Right? So that's possible. That has been done. If you are interested in that, also if you can, I can share some experience on that also. So okay, so that's it about telescope. So let me go to our next set of slides. That's going to be on astronomy software. So that's not going to be a long set of slides. Let's just talk about what the software we can use uh, for modern astronomy. So how the modern astronomy works. So if you have any questions, please drop in the chat while I get up with the next slide. Okay. You guys can see my screen now. This is going to be the second part of the session today. So this is some little information about the software that we use for astronomical observations. Okay, so observations and recording basically. So let's go through this. Anyways, if you guys have any questions about the previous part, just drop in the chat or maybe raise a hand so I can answer them. And also, if you have any like any questions for this part, also you can ask them. Okay, so astronomy software. So software is basically the most common use is hardware control. So almost every astronomical equipment has serial interfaces so that they can be controlled via PC. So the key part of astronomy software is to basically control hardware, so like control a telescope, control a camera, or control even a dome or maybe an observatory roof, right? It can be done through hardware. And another part that we do before observations is simulation. So we simulate the night sky to see what is visible, what's going to be happening in the sky, and then after the simulations, what we do is calculation. So if you need to know when is going to be the next eclipse, so when will be the next the occultation, when will the Saturn will be closest to Mars, right? Things like that. If you want to know that, you have to do the astronomical calculation. So there are tools for that, and also then the data collection part, data storage part. So that is basically imaging and data acquisition. There are the different software to do that and different software to process the data, right? So first one is the first one, yeah. First one is hardware control. So hardware control is mostly done through a protocol called ASCOM. ASCOM is the global standard for astronomical components. So that almost all the telescopes that are in the market support ASCOM. Almost all the PC software that is astronomy related support ASCOM. So this is a software platform that connects all the different applications and different hardware to basically automate imaging and automate data collection. So that is what ASCOM is doing. This is also free software, open source software. You can modify them, you can change them. So almost always, if you're serious about astronomy, what you are going to do is buy some equipment that you cannot manufacture, and then there's always a DIY part. So you have to fix some things, you have to adjust some things, you have to rig up some things that with the stuff you have. So ASCOM is always it's like a backbone for all those modifications, because it's open source. So you can edit the source code, edit the drivers, and do whatever you want. You can implement whatever protocol you want for controlling your hardware. So there's that. And then other part is simulation. So what by simulations what I mean is simulate the night sky. So what is in the night sky? That's what we are simulating. So we'll take a look at this software that we use for the simulation. So that so simulation software enables different viewing conditions like clouds and daylight and some moonlight and everything like that to see the effect on them on the observations. And also there are some other, these are the most popular software. So Stellarium is what we use. So your assignment will be based on Stellarium. And there are other, so this is also open source software from University of Strasbourg in France. So Cartes2CL is from Sorbonne, University of Sorbonne in France. And this Starry Night and CA are basically community run software. So they are also very functional, but the most user-friendly one and the most common one is Stellarium, right? So we'll base our assignment on that. I'll show you the software in a little while. And then comes the scientific component. So astronomical calculations. So how we analyze the data we collect, how we analyze the observations we do, right? So that is what the astronomical calculations do. So all these, this is how we enter astronomy. So what we do is buy a small telescope, install Stellarium, and see what's in this sky and try to spot them on the on your telescope. So that is the entry level infection of astronomy. So after a while, you need to build stuff, right? You're going to build stuff. You are going to automate your telescope. You're going to automate the software that you have to. So you don't have to point the telescope manually. So you can point it automatically. So you do that. So then you need ASCOM or hardware control, right? So then after that, you go into astronomical calculations. If you survive that hardware part, you can go into astronomical calculations. That is basically doing actual scientific data processing for astronomy. So most common uses of calculations are spectrography. Basically, identifying the elements that are in the celestial objects. So what is in the atmosphere of Jupiter? What is in that ring? What are the elements in the rings of Saturn? So that questions. The answers for those questions are in spectrography, right? Yeah, and the other one is supernova detection. So supernovas are, you know what supernovas are? They are the so basically that's the end of the life for a certain type of stars. So these are very spontaneous. So there are no warnings for supernovas. So they are very spontaneous. So what you have to do is keep observing and keep track the changes. So that's what you do. So I'll show you something I did in a little while ago. And then there are asteroid and comet discovery that is actually very feasible for amateurs to do, even without heavy equipment, without massive equipment. You can observe comets and observe see what they are doing, and and then tracking space debris. Also parts of empty spacecrafts and dead spacecrafts. That's also becoming a problem. So that can also be done using these calculations, right? So here is something that we detected, me and some colleagues. We detected that this was back in 2021 August. So this star, the pointing the arrow here, this star is not a normally visible star. So if you take the same, the same image in July of 2021, you won't see this. You won't see this star, right? So what we did was what I did was take random images and then store them and compare them after a few months with new images. So doing that, we discovered one of these new specks of light. So this is a new speck of light, a new object that has been formed within a few days of time, right? So this is a nova. So we didn't actually discover it. It was discovered way before us by professional astronomers, but independent of them, I think we did discover it independent of them, but after them. So that doesn't really matter. But anyways, so this is a nova. So that is again a star being exploded, but it's not as large as a supernova. So that's not a massive emission of light, but it's nonetheless it's a new event that was observed, that was detected using software. So what we do is, so these stars, they are not visible to naked eye, so you can look up and see them with the naked eye, right? So this is taken through telescope, a 16-inch telescope. So then what we do is we stack the images of the same sky and then compare each one of them for new specks of light. So for these new specks, maybe it's camera noise also. That can also be true, right? So then the camera has to be very low noise and very consistent with its color performance also. So that's part of the scientific component of astronomy, right? So that's one part. The other part is identifying objects. So if you take a image of the sky, you don't know what is there. You don't know the names of the stars, so you don't know whether they are nebulas or galaxies or whatever they are. So that's basically just a patch of sky with points of light, right? So you can use this website it's a web-based tool called NOVA to decrypt what is in the image. So this is the image I took in, I think last November. I think it is last November. So this is a patch of the sky called the Virgo supercluster. So there are thousands of galaxies here in this specific part of the sky, but I don't know whether what are the names of these. Right? I can't identify them each one by them manually. So what I do is use this tool, this NOVA tool, upload the image, and then it automatically annotates the image using international databases like the astronomical databases to show the galaxies that I found. Right? So what you can see is just patches of light. Right? So you can see some different things here, over here, and over here, and also over here, but it's still a bunch of stars. Right? Over here, something is something different. So it still looks like a bunch of stars. But if you analyze it with like actual scientific data, you can see that this every green patch here is a galaxy. Every green patch over here is a galaxy, right? So there are even hundreds of galaxies in single image. So identifying this cannot be done manually. That's impossible to do manually. So the only way to do is using astrometry or the astronomical calculation software, right? So the next part is collecting data. So this is how we collect data. Basically, you collect image data. So we have software to process images. We have software to plate so or generate annotation. That's what I showed you before, like generate annotations for this image. So what we do is we collect software to collect data from software, and also then process them in somewhat. So there are different astronomy specific software like these ones, PixInsight, MaxInTL, and AstroPixel processor. So these are astronomy specific imaging software. They can control cameras, they can collect data, and they can like denoise images and things like that. And also there are hardware control software specific to camera. So for Nikon or for Canon, and then also good old Adobe Photoshop to process images. That can be done. It has some scientific aspects, and it's definitely possible to process images with Photoshop too. So yeah, so those are software that we use for astronomy, and I think you got a slight idea about what's going on with the whole, like the practical component of observational astronomy. So how things are done, how things are calculated. So now let's move on to the software that I mentioned. So you can go to this website, www.stellarium.org. So it's a free software. You can download it for whatever operating system you're using, and you can install it. Let me see. Let me launch the software and show you what's there. Okay, I hope you can see my screen, right?
Yes, we can see.
You can see. Okay. Okay. So this is what you are greeted with the when you open the Stellarium software. So you can move around. We can move around with the cursor, right? Okay. You see why I'm stopped. Okay. So this ESC, and south, north, those are the directions. So those are the basic directions of the sky. So what you can see is what is in the sky right now. So let me see. So here is today's date, 2023, 26 April, and also current time. So this is the sky, exact sky above you, above your head right now. Okay. So, and you have to set the time zone also. You have to set that first when you start, you open the software, and then you have to set the your location. So this is my location. Let me show you that how to set those when you first install this software. So first you will, when you install this, it will default to its source location, that is the University Strasbourg coordinates. So you have to fix them first. So you have these are the major settings menus. First one is location. So you have to go here. You can search for your city here if it's available. You can search for your city here if it's available, or you can enter the manual here and then set your location, right? Then you go to the then, well, basically you are set for observations then, because everything else is taken from systems, from the computer itself. So you can start observing the sky, right? So the first configuration window is the date and time. So you can set any date and time to jump to that date. So let me see. Okay, so there's if you take my right in from my location, if I look west, I can see the Orion in the distance, right? Orion is descending. There's Betelgeuse, there's Sirius, and there's Moon and Pollux, and some star, and there's Mars also, right? What if I want to see what will be here in next year, exact same date, same time? So what I have to do is set this to this 2023. Now I can move it to 2024. Right now, this is the view of the sky in 2024, exactly a year from this moment. Right? Same time, same day, next year. Right? Let's see what I wanted. What was here when Portuguese are landing in Sri Lanka. So that is in 1505. So in 1505, April 26th, the sky was like this, right? If I was here looking at west, I would see Procyon here, I would see Saturn here, I would see Jupiter here, and the Portuguese will be landing in Gold Harbor, right? Okay. So that's what the date and time window does. So let's see. Have you heard of Halley's Comet? So Halley's Comet is a periodic comet that circles around every solar system every 76 years. So next one will be 2061. We don't know whether we will be here by then, but next one will be 2061. So let's see what will be there in 2061 when we are trying to observe the Halley's Comet. This will be the sky we are seeing. So Halley will be somewhere here, probably somewhere here in the sky, right? Okay, so that's what this date and time window shows. So let's come to, we can go back to the origin time right here. So that time to now on this one. So it comes back to the current time and date. So let's say I want to see the sky right here. Let's see here. What will be on the east? Today midnight. So I can set this to midnight. And midnight, the east will be here. So this is today. In 4 hours, this will be the view on the eastern sky. Okay, so there's the Milky Way, and there's the star Vega, and then you can see the sky simulated. Right? So I think that's enough for an introduction for software. I don't think I have to go through with about the software with you guys. So you can look through these controls. So this one is, you can change the viewing option. So what you want to see, you can see deep sky objects and markings and everything. So you can change those. Try changing those. And the next one is search window. So you can search for anyone you want to see. If you want to see the moon, let's say you want to see the moon, you can search for the moon. So it will automatically go to the moon. So now the moon is below the horizon, right? So you can remove the ground by pressing, you can remove the ground by this this button here. So ground can be toggled. So you can remove the ground or make the ground visible for more realistic view. You can keep the ground anywhere. So the moon is actually below the horizon, right? Next one is configuration. So basic settings for this. You can add new components, add new objects and things like that as they become available. And also, there's a calculations window to calculate what I told you, like the different phenomena. It was then like eclipses and occultations, transits, and things like that. So you can calculate them. And also, there's a help window. You can use that for that also, right? So this is all I'm going to tell you about the software. I think you can go through this, like have fun with this software and see what's going there. So the last thing I'm going to show is you click on an object. If you click on an object, this text will be all the details about that object. Right? So this is what you're going to need for the for your assignment. Okay, so if you see here, it's Vega, so this is star. Let's focus on that. So this is star, right? So it shows its name and its alternate names, like alternate names and scientific names. So this name Vega is basically an ancient name given to it. And then there are the details like type, magnitude, absolute magnitude, and things like that. So I think you know that all these, what magnitude is, what type absolute magnitude is from the previous lectures. So, and distance to Earth to 25.04104 light years. So things like that, right? So all the details are here. So you will need these details for your assignment on this module. Right. So I will leave you to read about the sorry, try and install and try out the software. So I will stop sharing now. Stop sharing the screen now. I think you can get a basic idea of the software by just using it. I don't think I have to explain software to a bunch of electronic engineers. So okay. So anyways, any questions? So just let me know what questions you have right now. You can drop in the chat or you can ask them away. Anything related to today's lecture or anything related to the software or anything? Okay. What would be the best location for astrophotography in Sri Lanka as you feel? So from my experience, ideal location in Sri Lanka is, let me show you in a map. I'm sorry if I'm taking too long for from your lecture, but I think it's you see you'll get the big picture why I'm saying this. Yeah, let me. So it has to be away from cities, away from all the civilization, and it has to be away from the sea also. Because sea salt is the worst thing for telescopes, worst thing for visibility. So let me share my screen. Can you see the map? Yeah, I think you can see them. So in here, this is the Yala National Park. So there's a reservoir called the Veharagal Reservoir. So this is the Veharagal Reservoir. Yeah? The best place I have seen in entirety of Sri Lanka is right here at the right head, at the bunt of Veharagal. There's a high bunt over there. No cities around, no power lines, no nothing. It's close, far away from the sea, and everything else here is like forest and no civilization, no city lights, anything. This is the, I think this is the farthest away you can get from a city or a crowded area in Sri Lanka, because everywhere else has a city somewhere close by, or either it's forbidden to go there in night. So this is the Viragalabant is the clearest place I've seen for astronomy. But basically, if you live in away from a city, from city lights and away from the sea, it doesn't matter. It's good enough to see the Milky Way by your naked eyes, and good enough to do good imaging. If you can manage the light pollution. Yeah, so that's the best place I see. Yes, the Shantas, how accurate is this kind of software? So if you choose 100 years from now, will it be accurate? Yes, that is the beauty of astronomy, because every movement, every motion in the sky is a mathematical equation, right? Because everything is based on either the rotation of the Earth around its axis, or the evolution of the Earth around the Sun, right? So any other movements, like the movement of Sun in the Milky Way, or the movement of Milky Way in the space, is far more in a far more slower scale than the time scales we are talking about. So from 100 years from now, it will be 100% accurate. The locations will be 100% accurate, unless they get destroyed by some like something artificial. Everything else will be pretty much accurate. Yes. Any other questions on this? Okay, if that's all, I think I'll upload the video somewhere and send you the link via Professor Rohan, so you can go through this if you want to. And also, I can share with you the slideshow also. And I did that with the previous pages also, so you can go through it if you like it. If you like astronomy, and if you want to learn a little bit more. So I think we can stop here if you don't have any questions. If you have any questions, let me share my email right here in the chat, so you can send me an email if you have any questions related to astronomy. Because it's not the most talked about hobby in Sri Lanka, and if you want to follow it, it's very difficult, right? Or nothing local, no local sources for reference, right? So if you need any information, just drop me an email. I think some of your colleagues have my emails too, because they are doing internship with Telecom. So okay, so I hope that I hope you learned something. I hope you got something out of it. And